How's it going, everybody? Today we're going to be solving a limit problem. It's a problem that I found in my calculus book that I thought was really neat. It was a very fun little problem. And it's relating taking the limit as theta approaches zero of the arc of a circle over the chord of the circle made by an angle theta. So let's go ahead and get started. Now, some of you probably already intuitively know the answer to this, which is great. That will give you a little bit of something to weigh your final answer with. But let's go ahead and write the arc length in terms of theta, as well as d, the chord, in terms of theta. So let's start with s, which is the arc length. And we know that s is r times theta. That's s equals r times theta. That's a trigonometry formula. At least that's when I learned this formula in trigonometry. And next we want to write d as a function of theta. Now let's go ahead and draw this as a triangle. You can relate d with theta with the triangle made here. And we know that these lengths on the left and on the right are r, which is the radius of the circle, and the chord is length d. Now there's two different ways that you can relate d, the chord of the circle, with theta. And there's no wrong way. In fact, there's probably more than two ways. There's these two ways that I can think of right now. There's no wrong way, but there's an easier way. And if you guessed law of cosines, yes, that would work, but it's going to take quite a bit more work if you were to go law of cosines. So instead of using the law of cosines, you're going to want to use the fact that if I were to bisect this triangle here, let me actually use a different color here. If I were to bisect the triangle here, I'm going to have an angle of theta over 2. And now we can use some trigonometry. This length here is going to be d over 2, and that is equal to r sine theta over 2. This right here is d over 2, this length over here, which means that we can rewrite d as 2r sine theta over 2. And I'm running out of space there. Alright, so we have everything we need to write our ratio, which is d right here as well as s over here. So let's go ahead and write this as a ratio of s over d. And it's getting a little crowded. Let me go ahead and move some stuff around here. Okay, so let's go ahead and write that ratio of s over d. So that's going to be s over d equals r theta over 2r sine theta over 2. And from here you can see that we can cancel some r's, which would mean that's equal to theta over 2 sine theta over 2. And now let's go ahead and take that limit. So the limit of theta approaching 0 on the positive side of s over d equals the limit as theta approaches 0 of theta over 2 sine theta over 2. Now, a lot of you guys might have already realized that this is a special kind of limit, and it could be made more apparent if I were to rewrite this limit as the limit of theta approaching 0 of theta over 2 divided by sine of theta over 2. And that's the limit we all know and love, sine of theta over theta, as theta approaches 0. It's the same if we were to flip them around, basically. So this limit is going to be equal to 1. And it makes a lot of sense too, because if you look closely at the photograph, imagine making theta smaller and smaller. Your d is going to be smaller, as well as s. Now, s and d are linked to one another. So D, the arc length of the circle, is going to kind of be inscribed in a sense. It's going to be squished into S as theta approaches 0, if that makes sense. But anyway, I thought this was a pretty neat problem. That's going to be it for this video, everybody. Thank you guys for watching. Let me know in the comments down below what you thought of this video. Should I make more like this? Did you like it? Did you dislike it? Hit the like button. Hit the subscribe button if you would like to see more like this in the future. And as always, I'll see you guys next time. Bye-bye, everybody.